Okay, good afternoon, everybody. Thanks for joining today's NCCAV seminar session. We have today's speaker, Benjamin Lerche. So he has been also give a similar talk yesterday in NCDOT Research Summit, and everybody was impressed by the talk that he gave yesterday. So the topic of his talk today is an efficient profit-aware large-scale vehicle dispatch framework for ride-sharing. Benjamin has been with NCCAV since I think 3.5 years or 4 years. Benjamin, correct me if I'm wrong. And he has been doing great research under Trust 3 of NCCAV, which is on using ride sharing for providing mobility services, on-demand mobility services. With that, I'm gonna pass it to Benjamin.
Thank you very much, Dr. Carmody. So I'll go ahead and share my screen. Yeah, so before I start my presentation, I would like to thank my advisor, Dr. Omuifa, and then I would also like to thank Dr. Karamudini, Dr. Bedada, and then Dr. Yen for contributing immensely to this project. And then as part of the NCCAV project, I would also like to thank Dr. Ann. Yeah, he has also been very instrumental in this project. So the title of my talk is An Efficient, Profit-Aware, Large-Scale Vehicle Dispatch for Ride Sharing. So this is the outline of my presentation. I'll first provide a brief background of the ride sharing problem, and I'll also provide some basic definitions that we use in this particular project. And then I'll also talk about the issues which motivated us to actually work on this project. And then I'll also provide the objectives and then challenges that we encounter whilst trying to solve this problem. And then I will provide a comprehensive description of our methodology. And then I also talk about some experimental results that we've obtained, and then the conclusions and then future work. So to start with, as a background of what ride sharing is. So basically, ride sharing or an on-demand ride sharing system consists of a fleet of shared self-driving vehicles in a centralized dispatch server receiving on-demand requests sent from passengers. So in this ride-sharing problem or this ride-sharing concept, the idea is to simultaneously allocate or assign multiple requests that are traveling in a similar direction to the same vehicle. So to explain this concept, we use this figure provided. So in this figure, we have 4 requests and then we have 2 vehicles. So what we want to do is how will we be able to assign the 4 requests to the 2 vehicles? So that's the problem we are trying to solve. So in this figure, for instance, the request 1 and then request 4 are sent to vehicle 1, and then request 2 and 3 are sent to vehicle 4. So this is just a brief background of the ride sharing problem. So moving on, I will provide details of how we assign the request to the vehicles. So another thing we talk about is some basic definitions that we use in this particular project. So the first one is a road network, which we denote it as a directed graph gene with a vertex set n and then an edge set a. So for each edge is actually associated with a travel cost. Where in this project we are considering the travel cost to be the profit. And then we also define a passenger as a pass request that has been picked up by a vehicle, and that is now en route to its destination. And then we define a trip as a set of requests that can be merged through ride sharing and served by a single vehicle. And then we also define another term called schedule. So schedule is actually the order in which a vehicle can pick up and drop off requests. And then waiting time is the difference between the time the request is sent or someone requests for a ride and then the actual time that the person is picked up. And total travel delay is the difference between the actual drop-off time and the traveling alone arrival time. So now, what are the issues or what motivated us to actually work on this project? So as we all know, in this our age and time, everyone wants to own a vehicle, which in transportation we call it personal mobility. Everyone wants to uh, everyone wants to own their own private vehicle. So by so doing, this has contributed to an increase in the number of vehicles that we have on our roads. And this has actually led to serious transportation issues like traffic congestion, environmental pollution, and then parking space availability. So to curb these transportation issues, there have been several research or there have been several solutions that have been uh, proposed. So one of them is what we call the on-demand ride sharing. And then aside ride sharing being able to, aside ride sharing helping to curb these transportation related issues, there are some other benefits that you obtain from ride sharing. For instance, service providers like Uber and Lyft are able to make more profit by serving more requests with the same number of available vehicles. And then with regards to the user or the person, once a person goes for ride sharing or prefers ride sharing, the person is able to pay less amount of money as compared to when the person is traveling alone, because the amount of money or the cost that the person pays is shared with other people that are in the same vehicle. So our objectives, we have two main objectives. The first one is to formulate the ride sharing problem as a profit aware problem. And then the second objective is to propose a vehicle dispatch, a computationally efficient vehicle dispatch framework for solving this problem. So to do this, there are a few technical challenges that we encounter. One of them is the large scale nature of the problem. So in reality, we consider like we can have several requests and we can have several vehicles. So once you are solving the assignment problem, it increases the search space of the different ride sharing combinations that you can have, and it becomes very computationally efficient to solve this problem when the problem instance or the problem scale becomes very large. And then another challenge is the how passengers are sensitive to the time of service. So as we all know, when we request for a ride, for instance, you request for an Uber ride, usually we wish the ride can be or the request can be attended to as fast as possible. And then another technical challenge, which actually is inherent when it comes to this problem, is the dynamic nature of the problem. The requests that will be assigned to the vehicles are not available to us at a go. So the requests come at different times of the day. So once we're able to solve an assignment problem, we solve the assignment problem, we obtain an optimal assignment of requests to vehicles. It doesn't guarantee that in the next time, that assignment will be the best. So to address these challenges, we've proposed a single request a single request badge assignment vehicle dispatch framework, which considers travel time. So this is an overview of our framework that we've considered. So first of all, we have requests are submitted periodically. So let's say for every 30 seconds, a certain number of requests are submitted. So we put all the requests that have been submitted within that batch period into a pool. And then we check for the status of the vehicles, the available vehicles. We check whether the vehicle can be able to take additional passengers or not. And then we compute a different request vehicle graph. We find different request vehicle pairs, which we call request vehicle graph. So for each request vehicle pair, we determine whether the schedule, which I've defined already as the order in which the request can be picked up and then dropped off by a vehicle. We check whether that schedule is feasible or not. If the schedule is feasible, we put all the feasible schedules into a pool. And then we use an assignment engine where we solve an integer linear program to determine the optimal assignment of the request or the schedule to vehicles. So that's a brief description of our framework. And then actually this is the algorithmic breakdown of what I talked about in the previous slide. So this is the overview of the vehicle dispatch framework. Once a set of requests are submitted, and then we check for the availability of the vehicles, we compute different vehicle request pairs, and then we find the feasible schedules, and then we use an integer linear program to find the optimal assignment of the schedules to vehicles. So algorithm 3 is used for finding the feasible schedule, and then to compute the feasible schedule or to obtain the schedule of a trip, what is done is once a request is received, we insert the origin of the request and then the destination of the request into the previous schedule. So to do that, we use algorithm 2 to insert the origin of the new request and the destination of the new request that have been received. So in our framework, we talked about obtaining a feasible schedules. So the question that someone may ask is, how do we get the feasible schedule? So we use some pre-test constraints. We have 3 constraints that we use to determine whether a schedule is feasible or not. The first one is the waiting time. So we set a certain maximum waiting time. So when the waiting time of a request exceeds that maximum waiting time, then that request cannot be included in the schedule. And then another constraint that we consider is the total travel delay constraint. So we set a certain total travel delay constraint such that once we estimate the travel delay of a trip, whilst considering a new request that has been received, if that travel delay exceeds the total travel delay that we've set, then that request cannot be included in the schedule. And then the final pretest constraint that is considered is the capacity of the vehicle. We have to ensure that we do not go beyond the capacity of the vehicle. So if the vehicle is full, we cannot add new requests to the vehicle. We cannot add new requests to the schedule of that particular vehicle. So there are actually two approaches or methods that are used in the literature. One of them being the multiple badge assignment, and then the approach that we are considering, which is called the single badge assignment. So in the next 2 slides, I will provide a distinction between how the multiple badge assignment is done and then how the single batch assignment, how we also do the single batch assignment. So I use these 3 figures or this scenario to explain how the multiple batch assignment works. So considering 3 different time states where requests are received for every 10 seconds. So for the figure on my left, or the figure on your left, we have 3 requests, we have 3 vehicles, and then initially, in the first 10 seconds, 3 requests have been submitted, which is request 1, 2, and 3. So what multiple batch assignment does is, it will group all those requests and then assign them to one particular, to a vehicle. So for instance, in the first 10 seconds, request 1, 2, 3 have been grouped and then assigned to a vehicle 1. In a similar way, in the next 10 seconds, which is when the time, like 20 seconds, and then 30 seconds. So for time period 2, requests 4, 5, and 6 have been submitted, and then they are grouped and assigned to vehicle 2. In the same manner, in the time period 3, request 7, 8, and 9 are also submitted, and then they are grouped and assigned to vehicle 3. Now let's see how the method we are considering, how different it is from the multiple batch assignment. So in the multiple batch assignment, for the first 10 seconds or for the first time period, the 3 requests submitted were grouped and then assigned to vehicle 1. But this is what we are doing differently. When the 3 requests are submitted, instead of grouping the 3 requests and then assigning it to one particular vehicle, instead we assign each request to a vehicle. So we do our assignment in a one-to-one manner. So as you can see in the other 2 figures, time period 2 and then time period 3, we are assigning the new requests that are received to the 3 vehicles in a one-to-one manner. So to perform the assignment, as I said previously, we are using an integer linear program. We solve, or the assignment is a solution to an integer linear program. So we have an integer linear program where the objective is to maximize the overall system profit. And then we have two constraints. The first constraint ensures that each vehicle will be assigned exactly one schedule. And then the second constraint ensures that each request can only be assigned to at most one vehicle. So as I said, we want to maximize the profit. So the profit that is generated from each vehicle is summed up to obtain the overall system profit. And to calculate the profit, we consider the fare that each request pays and then the compensation that a request receives. Find the difference between the fare that each request pays and then the compensation that the request receives. And then we subtract the cost of operating that vehicle to obtain the profit. So for instance, if like you have a vehicle that contains like 4 requests, so to obtain the profit or the profit that will be generated by that vehicle will be the sum of the amount of money each of the 4 requests pays. And then if in case the vehicle delays to pick one of the requests, that request receives a compensation or a discount. It receives a discount on their fare. So that's the penalty you are seeing there. And then the cost of operating the vehicle, you subtract it from the profit that have been made to obtain you subtract it from the fare that have been collected to obtain the profit that the vehicle generates. So moving forward, we talk about our experimental study where we compared our method with the state-of-the-art method by varying some important parameters. So first of all, we talk about the data set that we use. So the data set is actually provided by the New York City Taxi and Limousine Commission, and it has over 1 million instances. And then it has some features like the pickup and drop-off dates and times, pickup and drop-off locations, trip distances, and driver reported passenger count. So why do we consider this data? We consider this data because one, it has been widely used in the literature, and then two, the data is large enough to be used to test for the scalability or how well the algorithms scale to large problem instances. So these are the system parameters. So what we did is we varied like different parameters. So we have like maximum waiting time, batch period, then vehicle capacity, and then the instance scale. So we varied the maximum waiting time from 120 seconds, 180 seconds, 240 seconds, and then 300 seconds. The batch period, 5 seconds, 10 seconds, 30 seconds, 60 seconds. And then capacity of the vehicle being 2, 4, 6, and 8. And then for the instance scale, we wanted to check for the scalability of the algorithms. So we considered different instance scale. So we considered a scenario where the total number of requests will be 400,000, then the number of vehicles is 2,000, and then the number of requests is 600,000 when the number of vehicles is 2,800, and the number of requests is 800,000 when the number of vehicles is 3,600. So we're able to obtain some interesting results that we would like to share. So first of all, varying the maximum waiting time, we have these two figures. The first figure is how does the profit vary when we are changing the maximum waiting time, and then the second one is the response time, or how fast are the algorithms able to compute solutions when the maximum waiting time is varied. So as you can see, when we vary the maximum waiting time, or as we increase the maximum waiting time, the profit generated is also increasing, which makes sense because as you increase the maximum waiting time, it simply means that passengers or requests are tolerant or they are willing to wait a little bit longer. So if like you have you set a maximum waiting time of 2 minutes, a maximum waiting time of 5 minutes, that means passengers are willing to wait for up to like 5 minutes. So by so doing, we are able to serve more requests and then increase the amount of profit that is generated. So that explains why as the maximum waiting time is increasing, the profit that is generated is also increasing. And then another notable observation that can be made is the OSP. Sorry, I didn't explain this. OSP is the state-of-the-art algorithm, and OSP means optimal schedule pool. And then SRBAT is single request batch assignment with travel time, which is our method. And then the SRBAD is single request batch assignment with considering travel distance. So a notable observation that can be made is the optimal schedule pool actually generates more profit than our method, which quantifying it will be like 2.97%. However, in terms of computational time or the response time, the optimal schedule pool algorithm, which is a state-of-the-art method, increases way beyond that of our method. So another parameter that we varied is the vehicle capacity. So similar to the maximum waiting time, we vary the vehicle capacity from 2, when the vehicle can take up to 2 people, up to 4 people, up to 6 people, and then up to 8. So just like varying the maximum waiting time, you can see that as you increase the capacity of the vehicle, the amount of profit that is generated also increases, which also makes sense because if you have a vehicle of a larger capacity, it means you can pick up more people, provided that the constraints are not violated. And then you can also see that the optimal schedule pool algorithm, which is a state-of-the-art, outperforms our method in terms of profit by 3.87%. However, in terms of the response time or the computational time, our method is way faster than the optimal schedule pool algorithm, which is about nine times. And then we also vary the fleet size. So fleet size is the number of vehicles that we have. So we vary the fleet size from 1,000, 2,000, and then 3,000. So the amount of profit generated is still increasing, which also makes sense. If you have more vehicles, it means you can serve more requests. And then the optimal schedule pool algorithm. The optimal schedule pool algorithm has about 2.64% more profit than the single request batch assignment with travel time, which is our method. However, when it comes to the response time or how fast the algorithms are able to compute the solutions, our method far outperforms that of the optimal schedule pool algorithm. And then we also change the batch period. So the batch period, as I said, is the time that the request has submitted and then pre-processed. So we change it from 5 seconds, 10 seconds, 30 seconds, 60 seconds, and then 120 seconds. However, when we did that, we did not really notice any significant increment in the profit generated. And then the reason being that as you increase the batch period, it means, of course, more requests can be submitted. However, the pre-processing time has been increased, and then some requests may not be able to wait. So those requests may be rejected. So that explains why the profit generated is not increasing significantly when we increase the batch size. However, the profit that is obtained when the optimal schedule pool algorithm is considered is about 3.24% more than our method, which is a single request batch assignment with travel time. And then our method too is way faster than that of the state-of-the-art, which is the optimal schedule pool algorithm. So as I said previously, we also wanted to test for the scalability of the algorithms. Are the algorithms able to scale well when the problem size increases or when you have large problem instances? So as you can see, when we increase the problem instances, the profit that is generated is also increasing because you have more vehicles and then you have more requests. And then the optimal schedule pool algorithm, which is OSP, achieves about 4.81% more profit than our method, which is SRBAT. However, in terms of the response time or the computational time, our method is up to like 10 times faster than the optimal schedule pool algorithm, which is the OSP. So just to add up to the results, So our idea is to come up with an algorithm that provides a balance between the amount of profit that is generated and then the response time. So we also wanted to be sure, we wanted to check whether the profit that is generated by the optimal schedule pool is significant as compared to that of our method, which is a single request batch assignment. So we considered a certain statistical method that is used in the literature called Kolmogorov-Smirnov test. So this is we use this to analyze the significance of the profit generated by the optimal schedule pool algorithm and then the single request batch assignment, which is our method. So the null hypothesis was that there is no significant difference in the profit performance of our method and then the OSP. So when we computed the p-value, we obtained 0.7714, which is greater than the significance or confidence value of 0.05. Therefore, the null hypothesis is rejected. So there's actually no the null hypothesis is not rejected. So there's actually no significant difference in the profit performance of our method and then the optimal schedule pool algorithm. We also provided the big O notation of our method, or the computational complexity of our method, and then the state-of-the-art method, which is the optimal schedule pool algorithm. So if you remember in the experimental, in the results, the figures I showed, the OSP algorithm is computationally expensive as compared to our method. So here we are explaining why that is so. So the method or the steps that are considered in the optimal schedule pool algorithm is actually similar to our method. So in the OSP framework, there are 5 steps that are considered, which is the request vehicle graph, the request trip vehicle graph, and then computing schedules, and then solving the integer linear program, and then finally rebalancing. But in our method, we considered 4 steps. So we did not consider the step 2, which is the request trip vehicle graph. So as I said previously, the optimal schedule pool framework or algorithm is based on the multiple batch assignment. When the requests are submitted, group the requests first before assigning them to a vehicle. But we are saying when the requests are submitted, assign them to the vehicles in a one-to-one manner or one-to-one fashion. So grouping the requests actually contributes to the overall computational time of the optimal schedule pool algorithm. And then we've given the big O notation of the optimal schedule pool of the request tree vehicle graph, or the grouping of the requests together. So that the RTV graph, or the request tree vehicle graph, in the OSP framework runs in the time of O of V, KT, RTK, where V is the number of vehicles or the fleet size, and K is the capacity of the vehicle, and T is the number of all trips that are considered, and RTK is the number of requests in each in trip K. So in conclusion, I'm doing what? So in conclusion, we have formulated the ride-sharing problem as a profit-aware problem, and then we've proposed an efficient vehicle dispatch framework for on-demand ride-sharing. And our experimental results indicated that the proposed framework achieves comparable profit performance with the state-of-the-art vehicle dispatch framework. And then also the proposed framework is up to 10 times faster than the state-of-the-art vehicle dispatch framework. So in future, in the method I just described, or I just presented, that method is a centralized approach. So in future, we want to consider a distributed approach, where we will assume like you have a large city, like let's say Greensboro. You divide Greensboro into different sections or zones or regions, and then within each section or within each zone or region, we solve the ride sharing problem there. So we solve the assignment problem. We assign requests and we assign requests to vehicles in each region. without considering like the entire region, like as in a centralized approach. So we are hoping like by using this approach, we will be able to improve the computational time. So these are some references that we've considered in this work. And then thank you very much, and thank you all for attending my presentation, and I'm open to any questions and suggestions.
Benjamin, for the great talk.
Thank you.
So, any question to Benjamin? So, Benjamin, as far as the sort of, can you go back, or perhaps you mentioned it somewhere, but if you can, go back if that's the case, and remind me, how did you formulate the comfort of the current passengers in your vehicle in terms of um, not deviating so much from the travel time that they had in mind, and whatever, and compare to the sort of while you are meeting the maximizing the benefit as well. I think you had it somewhere in your problem formulation that
Comfort.
the service time for each passenger is not exceeding, while also you try to maximizing the profit.
Yeah. So your question is like on like the comfort, like considering the comfort of the passenger.
Yes,
So like comfort as in is the person willing to share a ride with someone like
correct. Yes, the
yeah
service
like
time, let's say,
references.
yes.
Come again.
I think you can quantify it in form of service time, correct?
Yeah, so yeah, we consider the service time. So but if like you say like comfort is also actually another avenue of research that people consider in this when it comes to like ride sharing. So like are the people like willing to share a ride with another person? So let's
Oh, I
say
see.
a smoker and then a non-smoker. Is a smoker willing to share a ride with a non-smoker willing to share with a smoker. But in this particular work or in this project, we are assuming we are not considering the preferences of the passengers. We are assuming the passengers are willing to share a ride with other people.
So, and then can you also comment in terms of if we wanted to go for sort of near real time calculation and vehicle assignment, can you, if you did it again, if you can walk me through those results that you had in terms of computation time or complexity?
You mean this one
Uh,
or the figures?
you had already the calculated the time already or not?
I don't.
For a given size of network, have you calculated the calculation time and to see if this is practical to be used for vehicle assignment in actual real applications or real time vehicle near real time vehicle assignment?
So like if I get your question right, you mean have I provided a mathematical representation of the computational time of the algorithm?
Either the complexity, if you have calculated, that's good, but if not, that's fine. Have you experimentally assessed the computation time and say, okay, for this size of network, this many yeah, maybe you
So
have it here, right?
that's the response time. So
Okay,
like the reason why I didn't put computational time like, in this, like every research usually have their register, like the kind of terminologies that is used.
Yep.
So yeah, in the literature, that's what is used, is response time. So that's why I'm using response time instead of like putting computation time.
Okay.
Yes, sir.
Response time. And what is in terms of second? What's can you
Yeah,
what is it there?
it's in terms of seconds.
Okay, in terms of second. So
Yes.
let me to see. So if we go with the very last group on the right side, can you comment on that? What is the three bars that you have there? Can you explain that?
Okay, so the first bar is a single request batch assignment with a travel distance, which is similar to our method. So, but for that, the profit is calculated based on the travel distance. And then the second bar is our method, which is a single request batch assignment with travel time. So we are calculating the profit based on the travel time. And then the third bar is the optimal schedule pool algorithm. That's the state of the art method that we are comparing our method to.
So
So
what you are claiming with a slight increase in the travel time, the middle one is yours, correct?
yeah,
So you are saying that with reasonable increase in computation time or service time, uh, you are not service time. What did you call it? Computation time. You said what? Okay. So with reasonable increase in computation time, you are gaining the quite significant profit based on the left graph, correct?
yes, sir, yeah, that's right.
Okay,
So the reason for that, distance, like the distance is fixed as
I
compared
see.
to like we are providing service to someone and then you are considering the time. And because the distance is fixed, when we are calculating the profit based on the distance, that would deteriorate in real life. Because assuming you are traveling from point A to B, right? Based on the traffic condition at that time, the travel time will vary based on the travel condition at that particular time.
Okay,
But with
I see.
distance, it's always fixed. Yeah.
Okay. So what is going to be next after this? What is the next challenge you try to address?
So in the one I just talked about is a centralized approach. So the all the requests are being sent to a centralized system or a centralized server, and then the assignment and everything is being done at that center. So the idea we want to consider is, can we allow each vehicle to determine where it can go or where it can travel to in order to pick up requests? And then can we be able to predict the demand or the request? So let's say Greensboro as example. Let's say we have a set of vehicles on campus, and then there is a high demand in downtown. So once we're able to predict or forecast that there will be a high demand in downtown at this particular time, then the vehicles can be dispatched to that location, can be dispatched to downtown to accommodate the high demand that will come up in that time in the future. So that's what I've been looking at currently, how to implement that.
But thanks again, Benjamin.
Thank you very much, Dr.
And thank
Kamini.
you everybody joining today's meeting, and everybody have a wonderful weekend.
Thank you, sir. Bye.
Thank you.